Remember, kids, the only difference between screwing around and science is writing it down.
So yours is
my heart.
Here, while you're here.
I was wondering.
Science isn't about the why, but why not?
Ms. Sarnt, what do you know about electron configurations?
What do I know about
Yeah,
electron
we need to know.
Is something like ion? No, I don't.
They make the infinity shape. Like the white girl tattoo.
It's obviously configuring electrons. I don't know anything. What are you talking about?
Not probably since high school or college.
You know how to say electron expand?
Is that a lie? Yo no sé, realmente.
How electrons are organized around the nucleus. The most stable pair, the most stable alignment being 8 electrons, which are found in the noble gases. An orbital is the containing of an electron pair.
Congrats on being the smartest so far.
Really?
Yep.
Wow.
What a fine day for science!
Behold, the periodic table of the elements, a representation of all basic substances that cannot be broken down further and retain its characteristics. But what gives elements their differing properties? Well, simply put, it's their unique electron configurations, which are the representation of the arrangement of electrons that are distributed among the orbital shells and subshells. The valence electrons, electrons on the outermost shell, are the defining factor for the unique chemistry of an element. The valence electrons are the ones involved in most reactions. This means that the different electron configurations give elements their differing properties, thusly is the basis of chemistry and why reactions take place. The 4 different orbitals, s, p, d, and f, have different shapes, and each orbital can hold a maximum of 2 electrons. The p, d, and f orbitals have different sublevels unlike the s orbital, and can hold more electrons, such as 2 plus 2 and so on. These positions are the volume of space in which electrons can be found around at about 95% probability. This is due to the Heisenberg uncertainty principle. The Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. This means that they have to have opposing spins in order to create the difference. A single orbital can hold a maximum of 2 electrons, which must have opposing spins in order to have the different numbers. If they didn't, they would have the same 4 quantum numbers, which is not allowed. One electron will spin up and the other would spin down. The s subshell has 1 orbital that can hold 2 electrons. The p subshell has 3 orbitals that can hold up to 6 electrons. The d subshell has 5 orbitals that can hold up to 10 electrons. And the f subshell has 7 orbitals which can hold 14 electrons. Now, musical songs of Bryce Aspie, telling you about the s, p, and f orbitals.
The s orbital is where it begins. Holds 2 electrons with opposite spins. Its shape is a sphere and its n equals 1. Keeps the electrons near like a baker and his buns. Now we're moving on to the p orbital. In an element like neon, its shell is full, shaped like a peanut with an n of 2. 3 different shapes and it can hold 6E. Now on to D, which has 5 different shapes. Some call it a donut, I think it's a bunch of grapes. 10 electrons to fill it to the top, but you better stop before it gets too full. The transition metals will just sit there looking dull. Don't you see, when the electrons can't move, the metal will conduct, and now let's groove on over to the orbital with 7 different shapes. The F orbital is a place electrons hate because it's so far away from the center. The positive charge can barely hold it together. This one can hold up to 14E, a flower or a firework, and an M will more than 3.
When assigning electrons to orbitals, each electron will first fill all the orbitals of the same energy level before pairing up with another electron in a half-filled orbital. This creates a more stable atom. This is best imagined as an antisocial bus where people tend to sit in unoccupied seats before having to sit next to someone when the seats run out. This rule is referred to as Hund's rule. Here is an example of Hund's rule, where each picnic table is a different sublevel of the p orbital, and each person is an electron.
Let's get ready to rumble!
Y'all ready for this?
I like to move it, move it. 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 I like to move it, move it.
Here is the off-ball process, where the people, being electrons, are occupying the lowest energy level before the highest, each stair-step being a lower energy level than the next.
Electrons first occupy the lowest energy levels and then move up to higher level orbitals once the preceding orbital is filled. When writing electron configurations, we are building up electron orbitals as we proceed from atom to atom. As we write the electron configuration for an atom, we will fill the orbitals in order of increasing atomic number. However, there are some exceptions to this rule.
Yeah, we're not doing those. To write the electron configuration, the energy level is written, then the subshell, which is either S, P, D, or F to be filled, and finally the superscript, the number of electrons in the subshell. It is important to note that the superscript is the number of electrons and is not the power, such as it is in mathematics. The number of electrons per atom can be found using the periodic table of the elements. It should be equal to the number of protons, unless of course you're writing the electron configuration for an anion or cation. There are 3 main methods used to write electron configurations: orbital diagrams, SPDF notation, and noble gas notation. The complete way to write a configuration is to follow the previously stated rules all the way through until all the electrons of the atom can be accounted for in the orbitals. This requires listing all the orbitals with their appropriate energy levels until reaching the outermost shell. This becomes quite time-consuming when entering elements with high amounts of electrons such as bismuth. The complete electron configuration for bismuth is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p3. That is quite lengthy. The orbital notation is shown here, which is the same as the previous, but is represented with arrows showing the electron spin as described by the Pauli exclusion principle.
I'm Olivia, here's my boss.
We're going to blow
outside. I know what to do. I'll type the noble gas configuration. Argon 4s2 3d10 4b4. Got it!
Right! No!
Yeah!
Noble gases have the most stable electron configurations because their outermost level is full, meaning their electron configurations are easier to write than those of the others. Using this, the common knowledge of the electron configuration of a noble gas allows us to use a short-handed method of writing electron configurations called the noble gas notation. To write in this notation, the noble gas preceding the element we are writing the electron configuration for is denoted, and then we will fill in the remaining orbitals using regular notation. The noble gas represents orbitals that have already been filled, so say that we wanted to write bismuth, it would now be xenon 6s2, 4f14, 5d10, 6b3, which is much shorter than the previous example.
What does the frog say? Get it down! What the frog say? What the fuck say?
For science.
Congratulations and celebrations.